Hello, good morning everyone. Myself Soumya and today we'll discuss about the pMOS transistor. So it is as shown in figure. You can observe that it is its operation is just opposite the NMOS transistor, whatever we have discussed in the last class. Here the n-type body is tied to a high potential. Okay, so the junctions with p-type source and p-type drain are normally reverse biased. So when the gate is also at the high potential, obviously no current flows between drain and source because both are at high potential means there will be no channel formed beneath the gate so that source and drain can communicate with each other. So when we apply the gate voltage which is lowered by a threshold voltage Vt, then holes are attracted to form a p-type channel immediately beneath the gate, allowing current to flow between drain and source. So the threshold voltages of two types of transistors are not necessarily equal. So we use the terms VTN and VTP to distinguish the NMOS and PMOS threshold. Now we'll discuss about the ideal IV characteristics of MOS transistors. In the last class itself, we have seen three regions of operations of a MOS transistor, which includes cutoff or subthreshold region, linear or non-saturation region, and saturation region. Let us derive a first order model, which is ideally Shockley model, relating the current and voltage for an NMOS transistor in each of these three regions. In the cutoff region where the gate to source voltage is less than the threshold voltage, there is no channel formed between source and the drain, so almost zero current flows from drain to source. In the other regions, the gate attracts carriers as we have taken NMOS transistor means the carriers or electrons are here. So this is going to form a channel beneath the gate between source and the drain. These electrons drift from source to drain at a rate proportional to the electric field between these regions. Okay. So if we know the amount of charge in the channel and the rate at which it is moving, then we can easily compute the currents. As we know, the charge on the plate of a capacitor is given by Q is equal to C into V. Thus, the charge on the channel, that is here we are going to name that as Q channel, is equal to the capacitance of the gate to the channel, that is Cg, into Vgc minus Vt, which is the amount of voltage attracting the charge to the channel beyond the minimum required to invert from P to N. By referencing the gate voltage to the channel, and here the channel is not grounded, okay, so then if the source is at Vs and the drain is at Vd, then the average is Vc is equal to Vs plus Vd divided by 2, or it is given by Vs plus Vds divided by 2. Okay, so the sum of the source voltage plus drain voltage whole divided by 2, or we can give that as the source voltage plus drain to source voltage divided by 2. Therefore, the mean difference between the gate and channel potentials VGC is VGS minus VDS by 2, which is as shown in figure. The average gate to channel voltage, it is as shown in figure. So the same thing will continue in the next class. Okay, thank you.